Okay, in today's video, we're going to talk about parametric curves. We're going to look at graphing parametric curves, how to switch between parametric equations and rectangular coordinates, rectangular equations, and then we're going to end with an application of parametric equations. So when we parametrize a curve, we are translating a single equation. We're translating a single equation in two variables such as x and y into an equivalent pair of equations in three variables, x, y, and t. One of the reasons we parameterize a curve is because the parametric equation yields more information. Specifically, it tells us not only the direction of the object's motion but also its direction over time, so there's path over time. So there will be three variables involved with parametric equations, and we'll be forming two equations. So each parametric system or group has two equations in it. So suppose t is the number on the interval of I, the set of order pairs x of t and y of t. So x is a function of time and y is a function of time. So x is a function of time and y is some other function of time. Forms a plane curve. That's what parametric graphs are sometimes referred to as plane curves, based on the parameter t. So t is called a parameter. The equations x of t is equal to f of t and y of t is equal to g of t are the parametric equations of this plane curve. So each plane curve has two equations, an x of t and a y of t. So we're going to find the parametric equation to the curve of the rectangular curve y equals x squared minus 1. We're going to let x of t equals t. So since x of t equals t, we can say that x equals t. So we can switch to our equation y is equal to x squared minus 1. We can replace the x with t, and we get y is equal to t squared minus 1. So that means we have now found a function of y in terms of t. So y of t is equal to t squared minus 1. So our parametric equations for this plane curve would be x of t equals t, and y of t is equal to t squared minus 1. Now let's look at sketching the graph of a parametric curve. The best way, or the easiest way to sketch the graph of a parametric curve that we will be doing in this year is just making a table of values. Remember, that's how you first started graphing rectangular coordinates. So we're going to pick some values of t. I'm going to choose -3 to 3. No real reason, just chose those three values. And then what you're going to do is you're going to take that t value of -3 and plug it into your x of t equation to get your x value. And so since x of t is equal to 3, that means x of -3 is just -3. So this column is the same as our t in this case, since x of t equals t. And then to find our y coordinate to graph, we use our second parametric equation, y of t is equal to t squared minus 1. We replace every t with -3. So -3 squared minus 1 gives us 9 minus 1, which is 8. So -2 squared minus 1 will yield a 3. Now, to sketch the curve of the parametric equation, we're going to plot these x, y points on our graph. But the key is, remember that parametric equations is doing over time, so we need to show some motion that's happening in our graph. We're going to do this by drawing arrows. Okay, we're going to start by plotting our first point. Our first point is the point -3, 8. So we're going to plot that on our graph. And then plotting -2, 3. -1, 0. 0, -1. 1, 0, 2, 3, and 3, 8. Then we're going to connect these dots with a nice smooth curve. And then to represent our function over time, we're going to put arrows on this that represent where we went. So from t equals -2 seconds, -3 to -2 seconds, I traveled down, and then I traveled around the curve and up. So notice that this is our parametric graph. Okay, they give us our x function with respect to time. And so again, that tells us that x is equal to t minus 1. So in my y function, I'm going to replace every x with t minus 2. I said t minus 1, t minus 2. And so simplifying this down by first doing t minus 2 times t minus 2 to get the square. So I need to fold that. Then distribute the negative sign and combine any like terms. So my parametric equations for this plane curve is x of t is equal to t minus 2 and y sub t is equal to negative t squared plus 4t minus 3. Now to sketch the graph of this, I need to make a table of values. Again, you're just going to pick different x values so that you can get a good look at the graph. I chose, again, negative 3 to 3, but that's not the ones you always choose. It's just always a good starting place to start with, as long as those values are in the domain of each of the parameterized equations. So this time plugging in negative 3 in place of every t in our x function, I get negative 5. Then plugging in negative 2 yields negative 4. Okay, next I'm going to go to my y function, replace every y with these t values. So for our first one, we're going to replace every t with negative 3. So negative 3 squared is 9. 9 times a negative is negative 9. Plus 4 times negative 3 is negative 12 minus 3, which gives us negative 24. Now to sketch the graph, we're going to start by making our xy coordinate plane. Now notice my x values only need to go from negative 5 to positive 1, so I don't have to do too much on that, but I do need to go down quite a bit on my y-axis, so I'm going to do my coordinate plane way up here, since I got to go all the way down to negative 24 on the y. Okay, so plotting each of these points on our graph, notice I'm only plotting my x and y because we're plotting on the xy coordinate plane. All right, so notice when I plotted these, I didn't quite get the whole parabola shape. So I know the pattern is going to continue like this, but you could have, this might be one which you could have extended out and evaluated a few more values of t, higher values of t, so that you can see this U shape. But notice that this is our parameterized curve for this function. Next, we're going to look at going the other direction. If I give you the parametric curves, the parametric equations for the plane curve, and we want to rewrite it into rectangular form, we're going to use a process called eliminating the parameter. Okay, in many cases, we may have a pair of parametric equations, but find that it's simpler to draw a curve if the equation involves only two variables, such as x and y. Eliminating the parameter is a method that may make graphing some curves easier. However, if we are concerned with the mapping of the equation according to time, then it will be necessary to indicate on the graph the orientation of the curve as well. There are many methods for eliminating the parameters t from a set of parametric equations. Not every method will work on every type of equations. We're going to focus on finding the methods of the most common types of equations. That's the polynomials, exponentials, logarithms, and trigonometric, and some basic trigonometric functions. Okay, so we're going to start by our first example. Now here we're given the parametric equations. X of t is equal to t squared plus 1 and y sub t is equal to 2 plus t. And we want to eliminate the parameter and write the parametric equation as a Cartesian equation, or rectangular equation is another word for that. Okay, so I'm going to choose the most simplest parametric equation. So I'm going to use the linear one. And remember that y sub t just means y. So we got y is equal to 2 plus t. I'm going to solve this for t. And I get that y minus 2 is equal to t. Then I'm going to substitute in what t is equal to in the other parametric equation. So you must switch equations. And so replacing t with y minus 2 and simplifying this down, I end up with that we have x is equal to, and then first thing I need to do is take y minus 2 times y minus 2. Using the full method, I end up with that is equal to y squared minus 4y plus 4. And then combining like terms, I have x is equal to y squared minus 4y plus 5. And this is the Cartesian equation, or the rectangular form of this parametric equations. All right, so you try this example. So pick the most simplest equation. Now we'll solve this equation for t. And I get that t is equal to 5 minus y. Then switch equations and go to the other parameterized equation. And we replace t with what you found it to equal to in terms of x or y, in this case y. and then simplify down. So I'm going to do my full method. And I get 25 minus 10y plus y squared. And then I'm going to distribute the 2 to everything in the parentheses. And last but not least, I'm going to add my like terms of 50 and 6 to get I get 2y squared minus 20y plus 56 equals x. And that is my rectangular equation for this parameterized curve. Okay, what if you have a logarithm equations? Well, it's the same process. Again, you want to pick the most simplest form, and it's usually the form that doesn't have the log in it. So I'm going to choose the x of t equation in this case. And so I'm going to rewrite my x of t equation, and I'm going to solve for t. To solve for t, I first need to isolate that t term, and then square each side. So I know that t is equal to x minus 2 quantity squared. So then I go to my y of t term, and I can simply replace the t in this term with what we found t to equal. So my y function, y equation, is equal to log of x minus 2 quantity squared. Now, we're not quite done. We're almost done. But notice that my rectangular equation, my Cartesian equation here, is a log, and it has a restricted domain. So I do need to restrict this domain. So I know that my x must be restricted, has to be greater than 2, because remember, it has to have a positive value inside of a logarithm. So make sure you check restrictions on these logarithms and exponential ones if it's necessary. Okay, I want you to try this zero term problem. So let's see how you did on this. To eliminate the parameter, and we're going to write this. We're going to choose the most simplest form of the equation. And the simplest form of our equation to choose would be the x equation. So e to the x is equal to e to the negative t, which I can rewrite as x is equal to 1 over e to the t. I multiply each side by e to the t, I get that e to the t times x is equal to 1, or e to the t equals 1 over x. I'm going to stop here. I'm not actually going to get t by itself. I can stop here because my y equation has e to the t, and so I can replace every e to the t with e to the t, and that works for me in this case. So don't do extra work you don't need to do. So let's go to our y equation, and in this y equation, which is 3e to the t, I'm going to get it in our Cartesian equation form, or rectangular equation form. I'm going to place e to the t power with 1 over x, and so y is equal to 3 over x, and you are done. Okay, if we're given a parametric equation in trigonometric form where we just have a one equation is in terms of cosine and the other equation is in terms of sine, or a cosine and b sine, we're going to use this technique. So I'm going to look at my x, and I'm actually going to solve for the trig function. So I'm going to divide each side by 4 to get that x of 4 is equal to cosine of t. Then I'm going to move to my y parameterized equation and do the same thing and solve for sine of t. And I get y sub 3 is equal to sine of t. Now, in order to work on this, I'm going to go back to our Pythagorean identity. Sine squared plus cosine squared equals 1. And I'm going to use that identity. And since it's sine squared plus cosine squared, it doesn't matter if I say sine squared plus cosine squared or cosine squared plus sine. I'm going to choose to write the x term first. So that means I have x over 4, that's my cosine squared, plus y over 4 squared is equal to 1. And distributing that square to the fraction, I get x squared over 16 plus y squared over 9 is equal to 1. And so it is a ellipse. So this rectangular equation of this a plane curve is this ellipse. So if you remember how to sketch ellipse from previous classes, our center is at 0, 0, and our a term is 4, so I'm going along the x-axis, 4 to the left and 4 to the right from the center. And then my b is 3, so from left to right, b is 3. So that would be my rectangular coordinate. Okay, so only thing left to sketch the graph of this parameterized curve is to figure out the direction in which we're going around the ellipse by looking at our time and plotting a few points. So I'm just going to choose our quadrantal points because they're really easy to do. All of those coordinates of sine and cosine are 0 or plus or minus 1. So it's easy to plug in. And we get the following points, which are the 4 points I plotted. But now I know the path it takes. It starts here and then goes around in this order. So since x of t is equal to 2 cosine of t, that means x is equal to 2 cosine of t. Solve that for cosine of t, and I get cosine of t is equal to x divided by 2. Do the same thing for sine of the y equation. I end up the sine of t is equal to y divided by 2. So using our Pythagorean theorem, I have x over 2 quantity squared plus y over 3 quantity squared is equal to 1, or x squared over 4 plus y squared over 9 is equal to 1. And there is our curve. I didn't ask you to sketch this one. Next, we're going to look at finding the parametric curves for curves defined on rectangular equations. So basically this is, since that's the equation in terms of x and y, I just have to choose one. So I'm going to let y of t be t. And so y equals t, so I'm going to replace every y with t in this equation. And then I get my second parameterized equation. So we're going the other direction. We start rectangular getting this. Now you can choose any value to start with. I could have made that as complex as I want, or simple. I highly suggest, save yourself some time, save yourself some stress. Pick easy. Pick it easy. Let one of the functions, one of your parametric equations just equal t. Life is so much easier if you just do that. Unless I specified, like I did on a previous example, and I require you to choose something, I want you to just pick t. Okay? The question is it going to be the y sub t is equal to t, or the x of t that's going to equal to t? And so in this equation, because it was x as a function of y, and y was my variable inside my equation, it made sense to make my y equal to t, my y sub t equation equal to t. So since y is equal to a function of x, I pick x of t is equal to t. And so I'm going to go to this equation y, replace every x with t. So now this is now a function of, y is now a function of time. And so I get that y sub t is equal to t plus 3 quantity squared plus 1. And x of t is equal to t. That is my parametric equation. It's that easy. Okay. Find the parametric equation of a line segment. So finding parametric of a line segment is a little bit harder. You have to use vectors. So that's the reason why we had to learn vectors before we can do parametrics. But once I go through the steps kind of explaining this, it makes kind of sense. So basically, I'm going to let A be my initial point of this vector, AB, and I'm going to let B be my terminal point. So to visualize this, I'm going to graph my A and B on the coordinate plane over here. And then I'm going to draw my vector AB, connecting these two, because that's kind of the line segment I'm finding. If I find the distance of that, I can find the lines, the equation here. So, oh, sorry, this asks for line, not line segment. So I'm going to draw a line all the way through A and B. Okay, now this is where it comes. Now I'm going to let O be the point at the origin. Now if I draw a vector from the origin to A, that's going to be vector AO. Initial point O in the terminal point A. And then if I draw a vector from O, the origin, to B, that's going to be the vector OB. Now remember that when we learned about vectors, and vectors addition or subtraction, vector AB is equal to the vector OB minus the vector OA. I'd have to do minus since those are, the arrows are not head to tail, but they're tail to tail. So I have to do subtraction instead. Now I'm going to choose another point on this line segment AB. I'm going to call it point P, and I'm just going to be a random point P, so it's going to be labeled X and Y. And then I'm going to repeat this process, but this time I'm going to do AO and OP as my line segments. And notice that OP, I'm sorry, not OP, AP, that should be AP. AP is a scalar multiple of AB. So as I said earlier, the vector AP is equal to the vector OP minus vector OA. Now let's find the component forms of vector OA. So since the initial point is 0, 0, terminal point is negative 2, 3, it's just going to be the component point is going to be that point A, negative 2, 3. Same thing with our vector OB. Our component form is 3, 6. And then we got to do the same thing for OP, so that means our component form is XY. So notice why, that's the reason why I chose that point to be at the origin. Makes life easier to work with. Now I'm going to look at this P equation, and I'm going to say, okay, well, OP is minus OA, vector OP, minus vector OA is equal to vector AP. Let me sketch this on the graph to make sense. So this vector here, and this vector AO, so vector OP minus vector OA gives us vector AP. And we know that vector AP is a scalar multiple of vector AB. So just plugging in our component forms into this statement, I get that the component vector xy minus the component vector negative 2, 3 is equal to t times the component vector for AB. Because AP is just it's a scalar multiple of AB. And that's where the t comes in. That's how we're introducing the variable t. I'm going to let t be that scalar multiple. And so to find vector AP, I just, find the component form of these two vectors where the initial side is at negative 2, 3, and the terminal side is at 3, 6. That means I need to subtract my terminal x value. I need to subtract those 2 points. And so now I'm just going to do scalar subtraction. Here I'm going to combine those terms, and now I'm going to distribute that t in to our vector. And so I end up with a vector x plus 2, comma, y minus 3 is equal to component vector 5t, 3t. So I got two vectors equal to each other. So that means the first component of the first vector must equal the first component of the second vector, or therefore x plus 2 must equal 5t. And likewise, the second component must equal the second component of the other vector. So y minus 3 must equal 3t. Solving each of these equations for x and y, I get x is equal to 5t minus 2, and y is equal to 3t plus 3. So this is my parameterized equation form of this line. X of t is equal to 5t minus 2, and y sub t is equal to 3t plus 3. And you are done. Now, the only difference between that equation and this one is, notice the first one asked us to find the equation of the line. This is asking us to find the equation of the line segment that begins and ends. So it's going to have the same parametric curve, except now we're going to have a beginning point and an ending point. So we have to find the x value that we start with, and the y and the t value that we start and the t value that we end with. So that's all we have to do. We just have to figure out it's not domain, but we have to limit our t values. And so to figure out this limit of my t values, all I really have to do, so to figure out these limited t values, I'm just going to start trying some t values until I get a x value of negative 3, my initial x value, and a y value of 3, my terminal y value. And so basically to do that, I'm just going to try some. So let's let t equal 0 and try that. So if t equals 0, x of 0 would be 5 times 0 minus 2, which gives me a negative 2. Oh, that's working out so far. And then y of 0 gives me 3 times 0 plus 3, which is also 3. So that gives me my initial point. So that's my first t value is at 0. So now I'm going to just start going up by seconds, by t values, to see where until I get that 3, 6. So I'm going to try t equals 1. And then I got lucky this time. My t equals 1 is my terminal point. But this had not been my terminal point. I would look at those values and decide if I needed to choose a value greater than 1 or a value less than 1. So you just kind of have to do guess and check until you find that work. So I know that by parameterization of this line segment with these following endpoints would be x of t is equal to 5t minus 2, and y sub t is equal to 3t plus 3, where t is between 0 and 1. So 0 is less than or equal to t, which is less than or equal to 1. And you're done with that type. So I want you to try this one. This time I ask you to find just the line through the point negative 2, 5 and 4, 2. So remember, our basic setup is vector OP minus vector OA is equal to a scalar multiple of vector AOB minus vector OA. So setting this up, that's just simplifying everything I explained in the original problem. If I translate each of these vectors to component form, this would be the setup of the problem. So that means using the vector subtraction or component subtraction here, I get the vector x plus 2, comma, y minus 5 is equal to the vector 6t, comma, negative 3t. And therefore, x plus 2 must equal 6t, or solving that for x must be equal to 6t minus 2. So x of t is equal to 6t minus 2. To get my y component, I just set y minus 5 equal to negative 3t, solve for y, and I get y is equal to negative 3t plus 5. So y sub t is equal to negative 3t plus 5, and that is my equation parametric equations for this line segment, or this line, sorry. All right, next we're going to talk about applications of parametric equations. Many of the advantages of parametric equations become obvious when applied to solving real-world problems. Although rectangular equations in x and y gives an overall picture of the object's path, they do not reveal the position of the object at a specific time. Parametric equations, however, illustrate how the value of x and y change depending on time and the location of the movement object, the location as a moving object as a particular time. One of the most common applications of parametric equation is solving problems involving projectile motion. In this type of motion, an object is propelled forward in an upward direction, forming an angle of theta to the horizontal, with an initial speed of v sub 0 and at a height of h above the horizontal. So if I wanted to find the parametric curve for this, I would start by saying x of t is equal to, the formula that you're going to use is v sub 0, initial velocity, times cosine of theta times t. And our y sub t is equal to negative 1/2 g times t squared plus v sub 0 times sine of theta, and all that term is times by t plus h. Now I introduced another variable I haven't defined yet, g. The variable g here is our gravity. And remember, so gravity will be 32 feet per second squared if we're in feet, and seconds is our units of study. And gravity is on Earth is 9.8 meters per second when we're in meters. So this is something you do have to memorize. And this is the effect of gravity on Earth, and depending on which unit of measurement you're looking at. So if we're looking at feet or we're looking at meters. So you have to decide by the problem which one to do. And you just replace that in that y sub t form in place of the g. So again, best way to do this is through an example. So here's the example we're going to do. This is the bottom of the ninth inning with 2 outs and 2 players on base. The home team is losing by 2 runs. The batter swings and hits the baseball. Does the batter hit a game-winning home run if the outfield wall is 400 feet from home plate in its deepest part of the park? Also assume that the wall is 10 feet high. Assume that the ball is hit with an initial velocity of 140 feet per second, and the angle is approximately 45 degrees to the horizontal. And we're going to make contact, and the batter makes contact 3 feet above the ground. So basically what this represents, so this is the batter hitting the ball. Here's the ball traveling, and one or two things can happen. It could be traveling like this, and then if we go to our wall that's in the outfield at the end of the park, there's our wall, and it could soar over the wall. It could be above the wall and soar over it and land outside. If it lands outside, hey, we have a home run. The other possibility that could be happening is we could hit the ball, and it follows this parabola path, goes this way as time goes by, but it hits the ground or hits the wall and never makes it over the wall. And if it doesn't make it over the wall, or hits the wall or hits the ground before the wall, no home run and they don't win the game. So this is kind of what the idea from the reading that we're getting. So let's figure out our parametric equation. So that's what A is asking us to do. So let's figure out our x of t and our y of t of this situation using those formulas I gave you above. So x of t is equal to the initial velocity times the cosine of theta times t. Memorize this formula. All right, so that tells us, and y sub t is equal to negative 1/2 g times t squared plus v sub 0 sine of theta, that all times by t, plus h. Let's figure out these values. V sub 0 is the initial velocity. So looking at our original problem, we see that the ball was hit at an initial velocity of 140 feet per second. So that's our V sub 0. So we can label that. Now let's see, theta was the angle which the ball was hit, was approximately 45 degrees from the horizontal. So theta is 45 degrees. Next, I need to figure out which g to use. So I look at my units of measurement in this problem. Unit of measurement is in feet. So I'm going to use the 32 feet per second. Per second squared, sorry. 32 feet per second squared. 32 feet per second, sorry. And then now I need to figure out h. Height is the height in which the ball was hit, and it made contact with the ball 3 feet above the ground, so the initial height of the ball was 3 feet. So h would be 3. Okay, plugging this information into our two equations, I end up that x of t is equal to 140 times cosine of 45 degrees, and that coefficient, that number, is times by t. And my y sub t equation is equal to negative 1/2 times 32 times t squared, plus the coefficient 140 sine of 45 degrees, all that times by t, plus 3, the initial height. And that's it. That's our parametric equation of this curve. Simplifying down, I end up that this is negative 16t squared. I need to go back and fix that. All right, let me fix this. I wrote this should have been negative 16t squared. So where is the ball after 2 seconds? So figure that out. We're just going to take our x of t function and our y sub t function and evaluate it at t equals 2, because after 2 seconds. So with our x of t function, I'm going to replace every t with 2. Okay, so I'm going to replace every t with 2. So replacing every t with 2 in our x function. And then punching this into my calculator, I get that x is approximately 198 feet. Okay, since x is our distance along the horizontal x-axis, this is our horizontal position of the ball after 2 seconds. Or the distance away from the batter or from home plate, or however you want to look at it. Okay, and then I'm going to plug in 2 in place of every t in the y equation and solve this with the aid of a calculator. I get y is approximately 137 feet. So this is the vertical position of the ball, or how high the ball is at the 2 second mark. So a way to write a sentence about this is, where's the ball after 2 seconds? So after 2 seconds, the ball is 198 feet from the batter's box and 137 feet above the ground. So notice we know exactly the position of the ball at a given time. That's what makes parametric equations so powerful, is that we can add that extra variable. How long is the ball in the air? So I need to figure out when is the ball in the air. Okay, and so to figure out how long the ball is in the air, I need to figure out when does the ball hit the ground. And whenever the ball hits the ground, that's the end. That's when it's over. And so remember, our height of the ball is determined by our y sub t function. So I'm going to take my y sub t function and set it equal to 0. When y sub t equals 0, that's when that's when it hits the ball. So I'm going to solve this equation for t. It's a messy equation, but it's simply a quadratic equation. Because notice I got a t squared, a t, and a constant term. So I'm going to solve this with a quadratic formula. With a little a from my calculator, I figured out that at t equals negative 0.03 seconds and at t equals 6.217 seconds, we have a y value of 0. So only the positive one makes sense in this situation. So my answer to this problem would be when after 6.217 seconds, the ball would hit the ground, or the ball is in the air for 6.217 seconds, however you want to state that. So now let's answer the final problem. Did they hit a home run? Did they win the game? Was he successful in bringing his team a championship here? So to determine whether the ball clears the wall, we need to calculate how high the ball is when it is 400 feet from home plate, because that's the distance the wall is from the home plate. And notice that the wall is approximately 10 feet tall. So distance from home plate, that is going to be the x component of our plane curve. And so I need to take the x component this time and set it equal to 400. And if I figure out what time, the exact time when the ball is 400 feet from home plate, that'll give us where the ball is at the time where the ball is 400 feet from home plate. So that's what we want to figure out first. And then it needs to be higher than the 10 feet wall, because if we don't get higher than 10 feet wall, then we got a problem. We hit the wall. So we'll start by finding out at what time the ball is 400 feet from home plate. So we're going to take our x variable and replace x of t with 400 and solve for t. So it's a linear equation. All I got to do is divide by that coefficient of t. So that means t is equal to 400 divided by 140 times cosine of 45. With the aid of a calculator, I end up that the t is approximately 4.04 seconds. Now, in the following calculation, I'm going to actually store this in my calculator, so I can use all the decimal values, or you could use the square root of 2 button knowledge here. But I'm just going to store this in my calculator. So I'm writing that ... to mean that, to let you know I'm not just using these decimals, but I'm using all the decimals in my calculator. So if I want to figure out, now I know when the ball is 4 feet from the plate, so let's figure out how high the ball is at that given time. So let's see if it clears the wall or not. So to do that, I go switch to my y equation, replace the t with that 4.04, and I end up 141.7755 feet. So that at the time that the ball is 400 feet from the base home plate, it has a height of over 141 feet. So it is soaring way over the wall. So the ball, how I can write a sentence about this, I could say that the ball is 141 feet in the air when it soars out of the ballpark. So therefore, my conclusion is it is a home run. With the bases loaded, they win. And this is an example of how we can use parametric curves to help us solve real-life application problems.